Hello everybody, welcome to today's session on quantum computing. This is the third and last lesson which is part of the R&D showcase. And this session has been split into two parts, part 1 and part 2. I'll be taking part 2. My name is Aryaman and I'm from your one and only ACM-VIT. And we'll start off by covering what qubits are, what a quantum bit actually means, and how qubits can be visualized using block spheres. And then after that, we'll move on to covering Dirac notation, which is like a handy way of representing quantum states. And then we'll move on to what an actual measurement means. So what does a quantum measurement mean? And I'm sure everyone must have heard of the terms superposition. So like when someone says a qubit can be in both states 0 and 1, what exactly does that mean? And after that, we'll cover quantum gates. And these quantum gates are the fundamental blocks which help you build quantum circuits and more. And we'll wrap part 1 by covering entanglement, which is actually quite an interesting topic. And then part 2 will be taken by my friend Manav Taluja, who will go on to teach the basics of Qiskit. And using the foundation built in part 1, he'll help you guys construct the quantum teleportation protocol. So without further ado, let's move on to part 1. Now, what are the prerequisites for this lesson? Well, you need to know what complex numbers are. You need to know that, complex number z can be represented by a real part and an imaginary part, where I is equal to the square root of -1. And then some fundamentals of probability. So, basics like the sum of all disjoint events is equal to 1, and this probability lies between, it's a real number which lies between 0 and 1 for all events. And you also need to know matrix multiplication. So, given two matrices, the given matrix A, which has W rows and X columns, and given another matrix B, which has X rows and Z columns, what output will you get if you multiply them? So now, with that covered, let's actually start with what a qubit is. And before we get to the quantum side of things, we need to discuss, what a classical bit actually means. So classical bits can either be in states 0 or 1, and they are physically implemented through wires. So you essentially have a wire with like electrons flowing through it, and the quantity given by the opposite side is called current. And you don't really need to understand what current means and what drift velocity is to actually understand Boolean logic, right? So in that same way, or we can say that 0 and 1 are like an abstraction of what is happening physically. So now if we went to the quantum side of things, this is what the qubit abstraction looks like. So this symbol is the Greek letter psi, and then this line in this angular bracket is called a ket, which we'll cover in the Dirac notation. So like a qubit can be represented as ket psi, or ket 0 or ket 1, and your ket 0 is analogous to the classical 0, and the ket 1 is analogous to the classical 1. So you might still be wondering how we'd actually physically represent a qubit, and this can actually be done in many ways, some of which have been described below. We can use light to actually represent a qubit. So there's a phenomena called polarization, and it comes in like two types, horizontal and vertical. So you could map like horizontal polarization to like ket 0 and vertical to ket 1, and then the superposition of these would involve ket 0 and ket 1. Or you can use an electron. So we know that an electron's spin is quantized, so it can be either plus half or minus half. So again, this can be mapped to ket 0 and ket 1. And you can also use the nucleus spin of a nucleus to represent a qubit. Now, again, as I talked about abstraction before, you don't really need to understand polarization or what nuclear spin means to actually perform quantum computation. So for this lesson, I just want you all to think of a qubit as an abstract entity, which is denoted by some phi. This will get cleared up soon. And with this abstract entity, we can perform computation or quantum computation, to be more precise. So now let's move on to the Dirac notation that I've been talking about for a while. This is also called the bracket notation, where if you have some letter A with this line and this angular bracket, this is pronounced as ket A. And then this over here is pronounced as bra B. And what this means is ket A just stands for a column vector, and bra B is just a row vector. And it turns out that if you first find the conjugate of some ket, and then if you find its transpose, then you get its bra. This is how it is being defined by definition. Now, conjugate transpose is just an operation that you can apply on a matrix. So you first find the transpose of the matrix. So like this 1 plus I will come down here, this 3 will go here, and then you apply the complex conjugate operation. So your 1 plus I would become 1 minus I, and your 4 minus I would become 4 plus I. So that's how conjugate transpose works. And in quantum mechanics, the conjugate transpose is also denoted by this dagger. So if I say A dagger, then it means first apply the transpose and then the complex conjugate. But the order doesn't matter. So if you apply the conjugate transpose on a ket vector, then you would get a bra vector. And now I've been saying ket and bra the whole time, but then what does a ket actually look like? So remember how we talked about ket 0 and ket 1? This is how ket 0 can be written. It's just a 2 by 1 matrix with 1 as the first element and 0 below. And then ket 1 is also another 2 by 1 matrix with 0 on top and 1 over here. And now, if you know matrices, you know that we can extend this to like an n by 1 column vector. And you can actually do that, and you can have, let's say d number of rows. And this abstract figure is called a qubit, with a d. And when you set d is equal to 2, you get a qubit. And we'll stick to d is equal to 2 or qubits for now, because that makes things simpler. Yeah. So now, coming to the topic of superposition. Now, you might have heard, popular explanations say that a qubit can be in both 0 and 1 state. And what that actually means is that a generalized qubit can be written as ket psi is equal to alpha times ket 0 plus beta times ket 1. So now your psi is, in this case, it's another 2 by 1 vector. Your ket 0 is 1, 0, and ket 1 is 0, 1. And your alpha and beta are two complex numbers. If you limited that to real numbers, it wouldn't change things by much. But in general, we deal with complex numbers in quantum computing. So what exactly does that mean? It means that to cover that, we'll move on to measurement. So when someone says measurement, saying quantum measurement on its own is kind of incomplete. We need to say performing measurement along a certain basis state. So basically, this is known as the computational basis state, ket 0 and ket 1. And physically, it can mean measuring an electron spin, or the nuclear spin that we talked about, the polarization of light. And if you had one vector psi, and if you performed measurement along the 0, 1 basis, then psi would actually collapse to either 0 or 1. So I'll just repeat that. When you perform a measurement along the 0, 1 basis, your arbitrary quantum state psi will either collapse to 0 or 1. And if you study probability, well, the probability with which it collapses to 0 is given by mod alpha squared. So this is what the alpha and beta actually stand for. Alpha and beta are called probability amplitudes. And then, since this is a complex number, you first need to find its mod. And then, once you find mod alpha squared, that's the probability with which your psi would collapse to 0. And similarly, mod beta squared is the probability with which psi would collapse to 1. Now we'll move on to the block sphere. Oh wait, before that, since this is a simple rule from probability, the probability of it collapsing to 0 or 1 should add up to 1. So mod alpha squared plus mod beta squared should be equal to 1. Now we'll move on to what, so far qubits have just been very abstract, like we have psi and then we have the superposition thing going on. But in what ways can we actually visualize a qubit? And one way of doing that is actually with a block sphere. So a block sphere is just a sphere with the positive z axis pointing to the get 0 state, and then the negative z axis pointing to the get 1 state. And so, for example, if you had a qubit like this, just this one sphere, and then if it's pointing upwards, along the positive z direction, then you can say that psi is equal to 0, get 0. And similarly, if it was downward, you can say that get psi is get 1. And just as a quick exercise of to see if you've understood it, if you had get 0, if get psi was equal to get 0, and then if you performed measurement on this along the 0-1 basis, then there is a 100% chance that this will collapse to just 0, because then alpha would be 1 and beta would be 0. So now, moving on to this, you can actually represent your qubit. We talked about how it can be represented as alpha times get 0 plus beta times get 1, but you can also actually derive this representation using a little bit of basic math and complex numbers. So as an exercise, try deriving this. And now what this representation actually means is, we've represented psi not in terms of its probability amplitudes, but in terms of two quantities, theta and phi. And through this equation, you can actually map what the block sphere looks like very easily, because theta turns out to be the angle between the vector, your quantum state, and the plus z axis. So this is theta. And phi turns out to be the angle between the state, the quantum state, and the positive z axis. And there's a few more other states that a qubit can be in. So for example, if your qubit was just strictly in the positive x direction, then you would write that as plus, so the get plus. And that's given by the superposition, so this is called equal superposition, because 1 by root 2 get 0 plus 1 by root 2 times get 1. So if you actually found, so here alpha is 1 by root 2, and then if you found its mod squared, you'd get half. So if a qubit is in state get plus, and then if you performed a measurement along the 0-1 basis, then there's a 50% chance that it will collapse to 0, and a 50% chance that it will collapse to 1. So that's what equal superposition means. And get minus is just the same, but it's along the negative x direction. Now, if you had your quantum state along the positive y direction, then that state is actually called plus I, or I plus. And again, that's similar to the get plus state, except that there's an extra imaginary component here, so I times get 1. And similarly, there's get minus, which is just along the negative y direction. So these states come quite handy to give an example for why this is useful. if you had a state in the ket plus state, and if you performed a measurement, then the probability of it being 0 or 1 is exactly 50-50, right? And it turns out that right now, no scientist has an exact explanation to why this happens. So, there might be some like hidden variables going on, or that theory has been debunked. So far the best explanation we have is that this collapse is truly random. So this is how you can actually prepare your own true random number generator. Your classical ones are actually called pseudo random number generators, and they use some kind of algorithm to produce random numbers. But with this, you can actually produce a true random number. If you produce the quantum state in ket plus and then just perform the measurement. So, okay, this is what I've been talking about. So if you had ket plus, which is given by 1 by root 2 and then times ket 0 plus 1 by root 2 times ket 1, then the probability of it collapsing to 0 is exactly 1 by 2. So that's what quantum measurement means. And now let's actually move on to quantum logic gates. So again, as before moving on to the quantum side of things, let's just review what a classical logic gate does. So if you had one classical bit, there are like a few operations that you can perform on it, So if you had a wire with like no current, you can just represent that as a bit equal to 0, and you can just leave it as it is, and then at the end you'd get 0, and then if your wire was 1, you'd just get 1. And then you can apply the classical NOT gate. So if your wire had 0 before, then it would turn to 1, and if it was 1 before, then it would turn to 0. And there's another operation called the fan out operation. So if you had one wire and then if you just split it, then you kind of cloning this classical bit. If it was 0, this would be 0, 0, and if this was 1, it would be 0, it would be 1, 1. And this is actually not possible in the quantum realm. And it's because of this thing called the no cloning theorem. Now, we won't be proving that theorem in this lesson, but the no cloning theorem basically states that you cannot clone an arbitrary qubit. So what I mean by an arbitrary qubit is, if you had like ket 0 or ket 1, these are like standard states, but then some, ket psi given by alpha beta, this is like an arbitrary qubit. So you can't clone an arbitrary qubit because of this. So similar to how you can apply classical gates, you can also apply a quantum logical gate on one or more qubits. And a quantum gate can essentially be represented using a matrix. And here's an interesting fact. All unitary matrices are valid quantum gates. So, why must the gate be unitary? Well, this is some homework for you guys. Why does it have to be unitary? Just find that out. And okay, what exactly does a unitary matrix even mean? First, your matrix needs to be invertible, so there needs to exist an inverse. And that inverse, so the inverse of your matrix U should be equal to its conjugate transpose, which is U dagger. Or you can just say that U times U dagger is equal to I. So what does this mean? I mean, from like a quantum point of view, classically you have like a finite, like very small number of operations that you can do on one bit, one classical bit. But if you had just one quantum bit, you can perform like, if there exists a unitary matrix, then you can just perform that on this bit, the qubit. So let's move on to some examples of actual quantum logic gates. So we'll start with the poly X, Y, and Z gates. So if you had the poly X gate, this is also called just the quantum NOT gate. So what the quantum NOT gate does is, if your qubit was in state 0, then it just flips it to ket 1. And if it was in ket 1, then it flips it to ket 0. So basically what it does is, ket 0 lies along the plus Z direction, right? So it performs a rotation about the x-axis by 180 degrees, or pi radian. And you can probably guess what Y and Z do. poly y, the poly y gate performs a rotation around the y-axis. So it will rotate like this, and that's also 180 degrees. And the same for the poly z matrix, poly z gate. And now we'll actually check out what it means to apply a gate on a qubit. So I'll show you guys the effect of the poly x gate on a qubit. So if you had the poly x gate times get 0, then you first write the gate and then you write what get 0 means, which is this 2 by 1 column vector, and then you just perform matrix multiplication. So 0 times 1 plus 1 times 0, you get 0, and then 1 times 1 plus 0 times 0, that's 1. So notice how this is actually equal to get 1. So we kind of converted this get 0 to get 1 using the poly x gate. And the same can be applied to get 0, as you guys can verify. So what does this mean for an arbitrary qubit? So if you had an arbitrary qubit given by psi is equal to alpha get 0 plus beta get 1, where alpha and beta are the probability amplitudes, then you can just say, okay, so what does this mean? Alpha get 0, it's alpha, and then this is get 0 plus beta get 1, and then when you multiply these two and add them, you get this 2 by 1 column vector. So if you apply the poly x gate on some arbitrary qubit, then you get 0 times alpha plus 1 times beta, and then which is beta, and then 1 times alpha plus 0 times beta, which is alpha. So notice how it actually reversed these two probability amplitudes. So before, if this was like 0 and 1, then it would become 1 and 0, kind of like how it did over here. And then if this was, let's say, if there was a 33.33% chance of the qubit collapsing to 0, then after this poly x gate, that probability will become 66.3% chance of it collapsing to 0. So I hope you guys can see how you can manipulate qubits, with these certain gates. And as an exercise, try verifying the effect of the poly y and z gates on any arbitrary qubit psi. So it's just basic matrix multiplication. You write the poly y gate here and then alpha beta, and then you multiply. So that's it for the poly x, y, and z gates. Now let's move on to the Hadamard gate. So the Hadamard gate is basically represented by this matrix right here, 1 by root 2 times 1, 1, 1, 1, 1, and then minus 1. And you know how I talked about converting some state to equal superposition, that's get plus. Well, the Hadamard gate is actually what helps you do this. And we talked about how useful get plus is and so on. So the way you apply this is the same as how you apply the poly x, y, and z gates. You first write the Hadamard gate, the matrix, and we're applying Hadamard on get 0 now. So get 0 is 1 and 0, and then if you actually multiply this, you'd get 1 by root 2 as the first element and 1 by root 2 as the second element. And this is actually the same as 1 by root 2 get 0 plus 1 by root 2 get 1, which is the plus get plus vector. And as an exercise, try verifying that the Hadamard gate is actually unitary. So reminder, a unitary matrix is one whose inverse is equal to its conjugate transpose. And find that inverse, just as an exercise. And similarly, you can also verify that if you applied the Hadamard gate on ket 1, then you would get the ket minus state, which is 1 by root 2 as the first element and minus 1 by root 2 as the second element. So now this gate is actually going to be very useful in the quantum teleportation protocol, and it's actually widely used in many algorithms because of the whole superposition aspect of it. And now we'll move on to the next gate, which is the controlled NOT gate. And this is actually our first multi-qubit gate. Multi-qubit gate. So, classically, if you applied NOT on some classical bit, then you're just applying this one gate on one bit, right? But then you also have other gates like AND, which actually work on two classical bits. So like that, so far we've seen single qubit gates, which act only on one qubit. But here we have, the controlled NOT gate, which is denoted by this amazing matrix. So it's kind of similar to the identity matrix, except the third and fourth rows are kind of interchanged. And the circuit is denoted by these two wires, which are qubits, with this small circle and this larger one. So this is actually called the control qubit, and this is called the target qubit. So before we actually get on to what the C0 gate does as a quantum gate, let's just look at it through in the classical sense. So if you had some like classical C0 gate represented like this, if your control bit was 0, then it would leave the target bit unchanged. So this is 0 and it's leaving 0 as 0. Whereas here the control bit is 1, so now it applies the NOT gate. So C0 stands for controlled NOT. So since the control bit is 1, your 0 will turn to 1. So that's what the controlled NOT aspect means. And then again, if your control bit was 0, then your 1 would stay as 1. But then if your control bit was 1, then your target bit will change from 1 to 0. So that's what it means in the classical sense. And before we get to how it actually works as a quantum logic gate, we need to figure out how to represent a multi-qubit state. And for that, I'll be explaining this operation that's called a tensor product. So the tensor product of two qubit states, so like, let's say if the first state was ket 0 and if the second one was also ket 0, then we can write that as ket 0 and then tensor product tensored with ket 0 again. And this is like a shorthand notation. And what this tensor product actually means is first you'll do 1 times 1, which is 1, and then you'll do 1 times 0. So 1 times 1 is 1, 1 times 0 is 0, and then you'll move on to the second row, and you'll do 0 times 1, which is 0, and then you do 0 times 0, which is also 0. So this 4 cross 1 column vector is what 0, 0 means. So now let's move on to the actual quantum C0 gate. So if you applied C0 on some 2 qubit state given by 1, ket 1 and ket 0, then you just write the matrix as it is. So this is the C0 gate, and first you want to find what the multi-qubit representation is. So you do ket 1 tensored with ket 0. So first you do 0 times 1, which is 0, and then you do 0 times 0, which is 0, and then 1 times 1, which is 1, and then 1 times 0, which is 0. And then you can basically find the product of these two matrices, the C0 and this thing. And when you actually find the product, so this matrix multiplication is very simple, you would get this 4 cross 1 column vector. And it turns out that you can split this 4 cross 1 column vector as the tensor product of 1 and 1. So just verify this really quickly. 0 times 0 is 0 and 0 times 1 is 0 again. So these two are 0. And then 1 times 0 is 0 and 1 times 1 is 1. So this is 0 and this is 1. So this is how you get ket 1 tensor product with ket 1 again, which again this 1 1 is like shorthand notation. And from a circuit point of view, this is what it actually looks like. Your qubit 1 is first ket 1, and then your qubit 2 is ket 0, and then after C0, the control bit is 1. So it's going to apply the poly X, if you guys remember that, poly X, which is the quantum NOT gate, to convert this get 0 to get 1. So you know how we just defined a C NOT gate, right? So C NOT stands for controlled and then NOT. Like that you can have like controlled anything, you know. You can have like a controlled poly X, which is C naught. You can have a controlled poly Y, controlled Z gate, and so on. So you can like play around with those and see how they affect qubits. And now let's move on to a very interesting topic. The final thing that we'll be covering is entanglement. And this is what Einstein described as spooky action at a distance. So what this actually means, we'll get to that in a bit. But before that, we'll first understand the mathematical formulation. You know, what does entanglement actually mean? Using the using states like psi and all, as we've seen before. So it turns out that not all multi-qubit states can be represented as a tensor product of single qubit states. So you know we had some psi 1 and then tensor product psi 2. So it turns out that not all multi-qubit states can be represented like this. And it turns out that if you can represent these two qubits as the tensor product, then these two qubits are not entangled. And if you can't represent them in this way, then these two qubits are entangled. So what entanglement means is that, you know, affecting one qubit will also affect the other one in some way or the other, which we'll see soon. So two arbitrary non-entangled qubits can be represented as this. So you know you have let's say one qubit psi 1. So if you had like two wires like this, and then if you had psi 1 as if qubit 1 was in state psi 1 and if qubit 2 was in state psi 2, then your tensor product of these two would be written as this. So you know psi 1 is given by the probability amplitudes alpha 1 and beta 1, and psi 2 is given by alpha 2 and beta 2. And you can actually like expand this and find what it looks like. So if this seemed very abstract, don't worry, we're going to solve a very small problem now to see if this state given over here is entangled or not. So I want you to actually sit down for a few minutes and work this out. You know, is this state phi plus, is it entangled or not? And a hint that I can give is that you know you can expand this and see if the system of equations makes sense or not. So just pause the video right here and yeah. So let's get to the solution. So now let's assume that you know phi plus is not entangled, right? Which means that we can write it as alpha 1 get 0 plus beta 1 get 1, and then tensor product with alpha 2 get 0 and beta 2 get 1. And then if you expanded this, then you know you just get alpha 1 alpha 2 times get 0 0 0, and then alpha 1 beta 2 and then 0 1, and then alpha 2 beta 1 and then 1 0, and at the end you would get beta 1 beta 2 times get 1 1. And now your initial question over here is the same as 1 by root 2 times 0 0. The shorthand for this is 0 0 and shorthand for this is 1 1. So I've just written it again over here. So these two equations should match, right? So now how do you actually solve this? So over here, if you can see, this this equation doesn't actually contain 0 1 and 1 0. So what this means is that alpha 1 times beta 2 should be equal to 0. And similarly, alpha 2 times beta 1 should also be 0, because these two terms do not appear in the final state. And similarly, if you have 0 0, then alpha 1 times alpha 2 should be equal to 1 by root 2. And then your beta 1 times beta 2 should be equal to 1 by root 2. So now let's try to actually find alpha 1, alpha 2, beta 1, beta 2. So let's assume that beta 1 is 0. Okay, so we'll take this, and for this to be 0, like one of these has to be 0. Right? So if beta 1 is 0, then alpha 2 can be anything. But then if beta 1 is 0, when we plug 0 here, we get 0 times beta 2, which is 0. So, beta 1 times beta 2 is giving you 0, which is not 1 by root 2. So you can't start off with this. So now let's choose the same equation again, alpha 2 beta 1, and instead let's take alpha 2 as 0. But then we can apply the same logic here, 0 times alpha 1, we took alpha 2 as 0. So 0 times alpha 1 is 0, which is not 1 by root 2. So this means that this system of equations is actually inconsistent, which means that the state given to us, phi plus, is entangled. And in fact, this phi plus state is one of the 4 Bell states. So again, as homework, try to find out what the other 3 are. You just have to swap certain values, like replace this with 1 and this with 0 and stuff like that. So now let's get to the physical meaning of what entanglement actually means. So if you had get phi plus, now we just found out that this state is entangled. So it turns out that if you perform, okay, so this state can be represented as a circuit like this. So this whole thing stands for this circuit. And now if you perform the measurement, so here I'll perform a measurement, and if this gave me 0, then physically this entangled state collapses to just this segment, which means that we can tell that on measuring this we also get 0. So I'll just repeat that. If you measured qubit 1 and if you got 0, then there's a 100% chance that on measuring 2 you'd get 0. And the same applies to this, Let's say you got 1 over here. So let's say, for a change, let's say you measured qubit 2. And if you got 1, then there's a 100% chance that measuring qubit 1 would give you 1. So that's what entanglement actually means. So I've just written that over here. And see, if you measured qubit 1 and got 0, then you can be sure that on measuring qubit 2 you will get 0. And the same applies for the other one. Now let's just take a quick preview of what's next. Manav will be covering the teleportation protocol, and there are a few difficulties that scientists have to overcome to come up with this. Because of the no cloning theorem, we can't clone any arbitrary qubit psi. And if you actually think about it, you cannot really clone phi just through measurements. This box with this line and arrow is a measurement. So if you actually measured a qubit, while measuring you don't know what alpha and beta are. You will just find out whether it collapses to 0 or 1. So to actually find phi or to find alpha and beta, you would need an infinite number of qubits in psi. So what that means is if you had an infinite number of qubits, and if they equally collapse to 0 and 1, then you can say that alpha is 1 by root 2 and beta is also 1 by root 2. But you can't be sure unless you have an infinite number of measurements, and that's not physically possible, right? So here's the problem that the teleportation protocol solves. If Alice has some arbitrary qubit psi, ket psi, and if she wants to send it to Bob, then how would she actually do it? So this can be separated through large distances as well. So if Alice is on Earth, and if she did some experiment and got psi, then how will she send this psi to Bob, who is on Mars? So to find out how this actually works, stick around for part 2. And I hope you guys found this interesting. Thank you.
Hi guys, my name is Manav and I will be delivering the quantum computing and Qiskit session today. So let us start by understanding what exactly is Qiskit. So Qiskit is an SDK or a software development kit. It is open source and completely free to use, and it has been developed by IBM. So using Qiskit, we can create quantum algorithms as well as run programs on real-time quantum computers that are currently at IBM's lab facility. So to get started with quantum computing, the first thing is that we need to actually have Qiskit on our systems. And to do so, we need to first install something known as the Anaconda distribution. So Anaconda distribution is a Python distribution, and we can download it by going to www.anaconda.com and then simply clicking on the download button, and you can customize it regarding any OS that you own. Maybe it may be Windows, it may be Linux, it may be Mac OS. So once you've downloaded Anaconda distribution, you'd simply go and type for Anaconda prompt. So the Anaconda prompt is basically like a command prompt. So whatever code, whatever commands you can run on your command prompt, you can run here as well. And you can also run a few commands that are peculiar to the Anaconda environment. So in my Anaconda prompt, I am going to type pip install Qiskit. So this takes a few seconds. So we're going to use the pip command to install the Qiskit Terra 0.2 package on our system. As you can see, my requirement is already satisfied, but once you run this command, if it runs successfully, you would have Qiskit on your system. So the next step we're going to do is open up the Jupyter Notebook. So Jupyter Notebook is an online notebook where you can write code, you can do live programming, as well as you can edit and share it with multiple people over the web. So to do that, we simply type Jupyter Notebook. So while working with Qiskit, I would advise you guys to open the Jupyter Notebook using the Anaconda prompt. And yeah, so it takes a few seconds. So as when the Jupyter Notebook would open, we're going to create a new file and just wait for it. So till then, let's just understand a few features of Qiskit. So Qiskit is an SDK, as I stated before, for quantum circuits. It is written in Python and it is designed to work with noisy intermediate scale quantum computers or NISQ computers. So as we can see, the Jupyter Notebook is open. This is its interface, and we're going to click on new and then open a Python 3 IPy kernel. So in this kernel, we'll see that we have certain blocks which we call cells, and we'd be writing our code within the cells. So we'd simply just save this as basic Python, basic Qiskit syntax. So now here in these cells, the first thing that we need to do is import Qiskit. So I'm going to type import Qiskit, and from Qiskit we are going to import all of its modules. So to move to the next cell in Jupyter Notebook, we simply press Shift plus Enter, and to move from one line to the other in the same cell, we press Enter. So I'm going to move on to the next cell. So with this, we have now imported Qiskit into our Jupyter Notebook, and the next step we're going to do is create a very simple quantum circuit using Qiskit. So for that, we need to initialize two parameters. The first is QC, and we're going to use the quantum register command. So this specifies the number of qubits that we would want to have in our circuit. So for example, we'll just create a circuit with 2 qubits. And then we're going to specify CR, which is the classical register. So the purpose of having classical register is that when you perform measurement on your on your qubits, so the value, whatever value is produced, you would like to store that in a classical bit so that you can maybe transport it, or then perform some operations and retrieve information from it. So that is why you specify something called as classical register. And now we're simply going to create our circuit, and to do that we're going to use the quantum circuit command. So we'll specify circuit is equal to quantum circuit and QC, CR. Let's write this as QR. So this should do it. So as you can see that our commands have successfully been passed. And to display this circuit, the next thing we're going to do is draw this circuit. Before we do that, we need to import matplotlib. So what this basically allows us to do is display whatever graph, whatever circuit that you want in Python's matplotlib library. So we're going to import that inline. And next thing we're going to do is draw this circuit. So circuit.draw output is equal to MPN. So as you can see, we have created a circuit with 2 qubits and 2 classical registers. And now what we're going to do is basically see a few operations or a few logic gates on these qubits. So before that, let us just refresh our concepts. So the 3 gates that we would be using a lot are the Hadamard gate, which is represented by H, the C0 gate, which basically acts as a XOR gate, and that is represented by a small circle which represents the controlling qubit, and the larger circle which represents the target qubit. And we would also be using the CZ gate, which is basically just a different orientation of the CX gate over the block sphere. So the first operation that we're going to perform is a Hadamard gate on the first qubit, and to do that we're going to type circuit.h and specify which qubit we would like to perform the operation on. So this, QR. So as you can see, the object has been created and our Hadamard gate has been applied. Before that, we'll just also apply the C0 gate with QR0 as the controlling qubit and QR1 as the target. So now we're going to display. So you can basically just simply copy this line and we're going to display the output of this circuit. So as you can see, we have applied the Hadamard gate on the 0th qubit, and we have applied a C0 gate from the 0th qubit to the first qubit. Now what we're going to do is we're going to perform measurement. So we're going to calculate the value from qubit 0 and 1, and we're going to store them in our classical registers. To do that, we're going to use the measure property, and we're going to type that circuit.measure, and we're going to write QR, and we're going to store that in our classical registers. Again, we're going to display this output. So as you can see, we are measuring both the qubits and storing their value in our classical registers. Now, before moving on, I would like to explain one thing. So this basic circuit that we have just now created is actually entanglement. So when you apply Hadamard, you apply superposition, and when you apply a C0 gate after that, you're basically entangling 0th qubit and the first qubit. So this is one concept that we would be using a lot later on when we're actually trying to implement Qiskit through the quantum teleportation protocol, but more on that later. So before that, we need to learn one more thing, and that is known as simulation. So in Qiskit Terra, we use a simulator known as an AER simulator. So for example, if you want to see your code and how it would run on a real quantum computer, but without any of the noise, so you can actually use Qiskit's simulators to run your code and then see the output. So for that, the first thing we need to do is actually import the AER or air simulator. So simulator is equal to air.get_backend, and we're going to import something known as a chasm or quantum assembly language simulator. So once we've imported the simulator, we will execute our circuit in the simulator. And we would use the result function to obtain a result from it and store that in a result variable. Great. So the next thing that we're going to do is, once we've obtained a result from our simulator, we need some sort of method to display it. Maybe a graph, maybe a line plot, maybe a histogram. So to do that, we will use the visualization library of Qiskit. So from Qiskit dot tools dot visualization, we will import a function called import plot underscore histogram. And then we'll simply plot a histogram based on the result we've obtained from. Sorry. So as you can see, we've obtained a result from the simulator and we've plotted a histogram based on whatever result that we've obtained. So this histogram basically signifies that there's a 50-50% chance or a 50-50% probability of getting either the 0 or 1 qubit. So now that we've seen the basic syntax of Qiskit, we can actually build something using this rudimentary knowledge that we've gained. And the thing we're going to implement is the quantum teleportation program. But before doing that, let us first understand what exactly is teleportation. So teleportation in simple terms is telecommunication plus transportation. So in classical world, we do that quite a lot, right? I mean, we're creating a copy of data, we're transporting it from one server to the other, and we're making different aliases of the same document, and we're trying to just send it from one location to the other. And this, although is simple in the classical world, but this is not something that we can implement in the quantum world. And the reason is that in the quantum world, we are guided by two laws. So the first is the Heisenberg uncertainty principle, which states that the state of a qubit cannot be ascertained with 100% accuracy at a given point of time. So we cannot know the state, we cannot know the position, we cannot know everything that we need to know to actually transport a qubit from one place to another at a given point of time with 100% accuracy. So that is one law that actually prevents us from teleporting a qubit from one place to the other. And the second is something which is known as the no cloning theorem. So we're going to see that. We're going to see the mathematical representation of the no cloning theorem. So the no cloning theorem basically just states that we cannot create multiple copies of an arbitrary state. And the reason is, so once if we can't exactly create a copy of a qubit, so how exactly would we teleport it, right? And if we do not even know the position of a qubit at a particular time, then how do we communicate it? Now the solution to these problems lie in a very simple concept that we've just seen right now, and that is known as entanglement. So entanglement can actually allow us to teleport qubits over space, and the reason is that because two qubits, when they are entangled, they are identical and they carry only one bit of information. And as soon as we read one qubit, the other qubit loses its data. So basically, we're not exactly creating a copy; we're simply deleting one copy as soon as we measure the other one. So before we actually implement the quantum teleportation protocol on Qiskit, let us first understand it more through an example, through a simple scenario. Okay, so let us assume that there are two people, Alice and Bob, and Alice has one qubit which is in arbitrary state. So arbitrary state is alpha times 0th qubit plus beta times qubit 1. So now Alice has this qubit which is in arbitrary state, and now she wants to transport the data or teleport the data which is stored in this qubit over to Bob, and Alice and Bob are miles apart. Okay, and the way Alice will do it, she needs to do it using a classical medium. So the reason why Alice cannot teleport it is because of the no cloning theorem, right? So now we need to devise a mechanism that allows Alice to actually send this information through Bob. So now if we keep in mind the concept of entanglement, we could actually easily solve this problem, and the way we do it is by introducing another qubit at on Alice's side, and we entangle it with Bob's qubit. So let us call it Alice's secondary qubit or an extra qubit basically. So when Alice's secondary qubit is entangled with Bob's qubit, and when we superpose it with Alice's arbitrary state qubit, this information, after that we measure it, is stored in that qubit, and this information through classical channels, through classical bits, can be transferred to Bob's qubit, and at Bob's side Bob can perform certain set of logic gates or unitary transformation and receive the information from this from Alice's secondary qubit. And as soon as he does that, Alice's secondary qubit collapses and the information is teleported to Bob, but Alice does not have any trace of that information. So now we're going to see how to actually implement this teleportation protocol on Qiskit. So to do that, we'll simply create a new file first. And we'll save it as quantum teleportation. So we'll quickly import Qiskit, and from Qiskit so now we'll create a circuit that comprises of 3 qubits, 2 on Alice's side, out of which one is the arbitrary state qubit, the qubit whose information that we have to send, and the other is the secondary qubit, or the qubit that would be entangled with the third qubit, which is Bob's qubit. So to do that, we'll take a parameter known as QR, and we'll take 3 quantum qubits, and we'll save them by the name Q. We'll take 2 classical registers, CRZ and CRX. The purpose of defining them separately would be clear later on. And then we'll simply create this circuit. So a circuit has been created. So before we display this circuit, we'll actually perform a few logic gates on Alice's qubits, and we'll define them as Alice gates. And the reason we're doing that is because at first we need to actually assign a certain amount of information to both the qubits before we actually entangle them with Bob's qubit. And the way we do that is by performing certain operations on them. So before we do that, we'll first entangle them. Define a function named as entangled, and we'll take three parameters. One is the circuit, the other is Alice's second qubit, and the other is Bob's qubit. And the way we perform entanglement is by a series of Hadamard and CNOT gates. So here we have Alice's second qubit as the controlling qubit and Bob's qubit as the target qubit. So now we're going to call this function and we'll draw this circuit quickly. So as you can see, we've entangled the first and the second qubit, which is Alice's secondary qubit and Bob's qubit. And the next step we're going to do is define Alice's gates and store information in Alice's qubit. The way we do that is by applying a CNOT gate first, followed by a Hadamard gate on Alice's first qubit. So here Alice's first qubit acts as the controlling qubit and her second qubit acts as the target qubit, and a Hadamard gate on Alice's first qubit. So before we do that, I'll also tell you guys a quick thing. So we can actually introduce barriers or divisions in our quantum circuit. So it basically just makes your circuit look much more cleaner and much more readable. So circuit dot barrier. And now we'll simply display, first we'll call the function Alice gates. So paste that function. So as you can see, we have now performed entanglement followed by storing information in qubit 0 and qubit 1. Now the next step that we need to do is measure these qubits. So now we're going to measure Alice's qubit and store its value in CRZ and CRX. So we'll define a function called as measure underscore qubits, taking the same parameters as Alice gates. And we'll simply measure. And we're going to call this function now. So as you can see, we have measured our first qubit or the arbitrary qubit at Alice's side, and we've stored its value in CRZ and we've measured the secondary qubit of Alice, and we've stored that in CRX. So now that we have stored the value into our classical registers, we will now obtain information from these classical registers, store that into Bob's qubit, and then perform certain gates on it. So to do that, we are going to define something known as Bob gates. And but before we do that, first we need to understand a few new concepts, and this can be represented here. So depending on whatever information we've received from our classical registers about Alice's arbitrary qubit, we will perform different type of gates. So for example, if we have 0 0, we will not perform any gate. We will Bob will receive the information as it is, and he does not need to perform any operations on his. And if we have a 1 1, then we will perform an XZ gate. So I hope that's clear, and depending on that, we will define Bob gates. So we'll now first we'll create another barrier. Can define that later. First we'll define Bob gates. So here we have defined, we're taking 4 parameters. The first is our circuit, the second is Bob's qubit, and the 2 classical registers next. So here we'll define our operations. Okay, now, so what this code exactly does is that it performs a Z gate if the value stored in our classical register 1, or the classical CRZ is 1, and it performs an X gate if the value stored in our classical register X is 1. And this C if gate is basically, it allows you to it's basically a C0 gate that allows you to control using classical registers rather than your normal qubits. So I hope that is clear. So again, as I stated before, 0 0 no operation, 0 1 X operation, 1 0 Z operation, and then 1 1 XZ operation. So now that we have defined Bob gates, Bob underscore qubit. Sorry, my mistake. So now that we've defined Bob gates, we'll call this function. We'll create a barrier first. And we'll call Bob gates. And we'll draw this function. Okay, as you can see that we have now performed operation on Bob's qubit, and we are retrieving information from CRZ and CRX by Z gate and X gate, and we have now created our final quantum teleportation protocol circuit. So as you can see, we have now taken the information from Alice's arbitrary state, we've decoded it, we've entangled Q1 and Q2, we've measured Q2, and we've destroyed whatever information was stored in Q1, indirectly destroying whatever information that was stored in Alice's arbitrary qubit. And in this way, we are not breaking the no cloning theorem, and we have also performed our teleportation. So with this, we have reached the end of this presentation. And as a fun task, we've learned about simulators before, and the way it's a fun assignment if you guys are up for it. You can actually simulate the circuit by taking a few extra parameters and run that on a real quantum computer, and actually retrieve other information such as a histogram plot, or any other block sphere plot, or a q plot, or any other information